there's like that, you'll always be
Okay,
learning
that's
things.
Gary McMurtry. I'm Jay Fidel. We're doing research in Manoa. We do this every Monday at 1 o'clock, you'll see. And we have the most interesting people come on the show. You know, Manoa is loaded with people like Gary McMurtry doing this fabulous work.
Oh, thank you.
World class. I boast about it everywhere. I'll tell you the truth. It's beautiful what you guys do.
Oh, well, we appreciate the flattery.
He's a professor of oceanography. We have so much good oceanography going on here. We're world famous, you know, that's the truth of the matter. He can be modest if he wants, but that's what's going on. Anyway, today we're going to talk about, what was it now? Predicting seismic events through dissolved gases.
That's right.
So we need to not only know about the dissolved gases and have a handle on how that works, we have to take that to the next level and be able to measure the dissolved gases and then predict seismic events that are happening and warn people about them.
Right.
And this is yet another technology which will save lives.
Yeah, it could, and that's why we're pursuing it. You know, it's, the key word there is prediction, and prediction always means, you know, you have to do a lot of background work to understand it, and it's a very daunting project, but I think we have the technology available now to attack it, you know, to actually pull it off.
Yeah.
And like I say, prediction means you have to have something out there already measuring. You can't just do it after the fact collections. A lot of that's been done, which proves it can work in theory.
Yeah.
But to get to a hazard assessment, you actually have to be able to go out there and put the instrument in the field. And that's what we're trying to do.
So that'll give you the flavor of what Gary's doing.
Yeah.
We're going to get into the weeds on this.
Sure.
You know, chemically and instrumentation-wise.
Well, I've been doing this stuff for about 15 some odd years now, maybe even closer to 20
Tell
now.
us about the 15 years. Tell us how you got to be a scientist. You know why? Because they all want to know.
Really?
They want your
That's easy.
job.
Okay.
They want to follow your tracks.
Well, if you want to be a geological oceanographer, which is what I am, a geologist is what you have to be first. And geology started for me with just going out, and I was born in Southern California, and my parents would take me on trips to the desert, trips to the mountains, and mostly in the Mojave. I got really interested in the rocks and became a rock hound, first of all, and then later I found some dinosaur bones, and that was just like it. You know, I was totally hooked when I had found dinosaur bones and trilobites and things like that, and petrified wood. So that's how it started, as a rock. And then I'm one of these few people, I think, not that actually knows what they want to be when they're like 5. I knew I wanted to be a geologist, and so it was just like a total career path for me to get my degrees in geology. So, and I ended up doing that here in Hawaii.
Where'd you go to school?
Yeah, well, I got my graduate degrees in Hawaii, both my master's and PhD, and there we were looking at, you cannot ignore the ocean. We're surrounded by it. So I was interested in volcanoes. That was one of the things, an obvious segue off of the rock collections and all that. And then I got interested in just broad scale, what's going on in the ocean, hydrothermal vents, hydrothermal plumes. All that was going on in the 70s. Major discoveries were going on. And I was fortunate enough to be, you know, in the right spot at the right time.
It's the right place, too.
Yeah, they're absolutely one of the best. And so we were at the forefront of a lot of the pioneering research on hydrothermal vents and origin of life at vents, chemolithotrophic organisms.
You know, there came a time when you started getting interested in measuring gases in the seawater, in the ocean.
Yeah, that started about...
What turned you on to that?
Oh, we were studying Loi'i, you know, our little backyard submarine volcano. And we got to the point to where every time we went down to collect samples of the hydrothermal vents, we'd get a different data set. And this was very interesting to us. Why is the slopes of all the curves changing all the time? So we wrote papers on that based on sample return, where we would bring samples back to the lab and analyze them. And then it became clear if we really wanted to get a handle on it, we should be there all the time collecting. And that meant instruments. And it's been a long time since that desire back in the early 90s to come up with an instrument that can be deployed in a place like that.
I want to talk about the decision process that took place with you, because, you know, I talk to scientists from Manoa like every week. And it just seems to me that there's a point where they're out there and they're looking at various sciences, maybe teaching, you know, doing projects, but they haven't settled on anything. And then something happens on one thing, instrumentation of gases for you, but it's always something. And then then the fellow puts his career in on that. So
It
what
happens.
is it that makes, you know, instrumentation and gases your central point in science?
Frustration. That's what it was. I was
Okay.
totally frustrated. I started looking around the early 1990s at what was available to put on low E. I mean, we had the dives. We had the HURL program giving us submersible dives, and we were very grateful for that. And we were putting down everything we could, but it was all, the state of the art was a CTD in those days, which is a, you know, stands for continuous temperature depth unit, and it has a little conductivity sensor on it and a temperature sensor. If you can soup them up, you can get a depth sensor that's very, very precise, and we did all that, and we figured out ways which we measure radon, which is a radioactive gas that comes out of the ground, and so we had those things going for us, but anything else was just forget it, especially if you wanted to go deep. In those days, I wanted to measure pH at 1,000 meters. It was impossible. Nobody had anything go below 400 meters and would last for more than a few months.
Are you saying it's possible now?
Oh, absolutely.
Oh, my
Yeah,
goodness.
technology is really advanced now. So they have optrodes that can do pH easily at 1,000 meters, and they'll last a long time. They don't drift so much. So they've come a long ways with that, and they have other sensors now with CO2 sensors and dissolved
Can I go
oxygen.
back to
Sure.
the pH?
Yeah.
How in the world do you tell what the pH is 1,000 meters away? That's 3,000 feet
Yeah,
away.
yeah.
How can you possibly tell?
Well, I mean, you have a device that originally is just like the normal pH electrode you use in the lab, and it's all saturated with water, so it has a solution, so it won't crush. That's a good thing. The problem with those kind of technologies is that eventually, even in the lab, the electrolyte will diffuse into your sample and becomes, you know, it drifts. It doesn't read the same readings when it does that. So you have to pull it and put a new one in. We're still pulling instruments and putting down repaired instruments. That hasn't changed, but we're getting better and better at being able to make all the kinds of measurements we really want to make. And now we're just, you know, now it's the other way, the shoe's on the other foot. Now it's like we have the instruments, but it's hard to get the dives. Isn't that crazy? I mean, before we used to have lots of dives and not the instrument. So we're in a kind of a funny flip-flop on that.
Well, I want to just explore with you this whole thing about frustration.
Mm-hmm.
You know, because it comes up over and over again, where a scientist is into one area,
Mm-hmm.
and he wants to go further in the area, but he finds he needs instrumentation or maybe software or a combination of things.
Yeah.
And he says, what am I going to do? I got to get through this. This is holding me back. So he says, well, I'll do what creative people do. I'll build it myself.
Yeah,
And
that's
it's
true.
not necessarily what you studied in geology either.
No.
This is new material.
No, I
And
wish
you had to crack a book on that.
I wish I'd taken an electronics course when
Really?
it would have really helped. You know, one of my secrets is that I work with people who do know electronics, and they help me. And I've been very fortunate in that regard. I have a team that helps me get what I want to have. So,
With a team.
well, there's engineers at UH at SOEST there.
Yeah.
We have an engineering support facility. They have very good engineers. We have good machinists there. These are all our secret, so we really don't want to broadcast them too loudly, too widely.
Yeah, forget everything you're hearing.
Yeah, I didn't say that. But we have, you know, people we've met all along the way, and you keep them as friends and colleagues. And when a job comes up, you know, usually it's a combination of, I can give you some money, please, you know. And so it's because we're all busy, and you have to try to sneak your little pet project in. So it's like a lot of that
That's
goes
the
on.
power of collaboration.
Absolutely. I mean, this money is just one way of coercing somebody to get them to
Yeah.
do what you want to do. There's many other ways too.
But they love it, don't they?
Oh yeah,
They
absolutely.
love helping somebody.
I think they always appreciate it, especially if you mention who they are. And in the end, you know, everybody appreciates the fact that it works. A lot of times it's just fun to get it to work. And I mean, one of the things I've always tell people, you know, I have very, you know, low expectations sometimes. We're just like, wow, it came back and it's not full of water. You know, his instrument's still dry inside. That's a biggie.
Yeah.
That's an important one. And so, you know, beyond that, it's does it function and does it give you some data that you expected? So that's the level we're at. It's a very challenging environment. You know, it's high pressure. You make one mistake, have a a very small crack somewhere in a housing, in a penetrator, and you can lose your whole project.
How deep do you have to go with it?
Well, on Loi'i, most of the action's at the summit, which is about 1,000 meters. But if there's a deep hydrothermal field that people have been looking at, some of my colleagues, in fact, in the oceanography department, it's down about 5,000 meters.
Wow.
That's pretty deep.
So any tiny crack and
it's really unforgiving, especially at those pressures. Yeah, at the bottom, it's very, very high pressure. It's a whole different realm working at the very deep ocean.
Well, I want to take a short break, Gary, and then we'll come back and look at your slides and see exactly what this is all about and give people the flavor of what it took to put it together.
Thank you.
Okay, we'll be right back. That's Gary McMurtry of SOEST.
Hi, I'm your host on ThinkTech Asia, Bill Sharp. I look forward to you joining us each Monday between 4 and 5 o'clock when we film right here in our studio in downtown Honolulu. The show, ThinkTech Asia, focuses on contemporary events in Asia, and by Asia we mean anything from Hawaii, south to Australia and New Zealand, west to Pakistan, and as far north as the Russian Far East. Clearly, this is one of the most economically dynamic centers of the world, and we bring you up to date on what's going on in a whole host of countries in this very vital region. We look forward to seeing you. Aloha.
Hi, my name is Cindy Matsuki, and I host the show High Growth with HTDC on ThinkTech Hawaii. This is the show where we talk about all things tech, innovation, entrepreneurship, and manufacturing, because there's so many things going on in Hawaii and more people should know about them. So this is the program that you can come and find out about all the things happening in Hawaii. And this show also airs on Olelo 54 along with ThinkTech Hawaii. And it broadcasts live every other Tuesday at 3 p.m. So don't forget, check out the show Tuesday, 3 p.m. every other week. High Growth with HTDC. Thanks.
Okay, we're back. We're live with Gary McMurtry of SOEST, a professor of oceanography there.
Professional, yes.
And for 15 years, he's been working on instrumentation that would allow to measure the different kinds of helium gases. Am I right?
Right.
And thus, use the data that you get from measuring the difference in these helium gases to figure out seismic events that are happening or will happen.
Right, because helium is especially interesting for our use, for understanding the Earth's processes, because it comes from the upper mantle, at least the helium-3 does. Helium-4 is in the crust, but most of it. But the helium-3 component comes from the deep mantle, and that lets us, and besides, helium is very light. The only thing lighter than helium is hydrogen. So, and hydrogen is reactive, so because helium is both very light and a noble metal, it doesn't react with anything, it just has a very long pathway. So you can see very deep into the Earth with helium. And so we look at these two isotopes. They're both stable, they don't decay. There's helium-4, which is, we wouldn't have any helium on the Earth if it wasn't for the fact that we have a lot of uranium and thorium in rocks, especially the crustal rocks, that decay by alpha and are always producing helium-4. So we have a big helium-4 background.
And that's an atom. You're describing an atom.
Helium-4
Helium
is an atom.
Periodic table of
That's
elements
correct.
And everything.
Yeah, and there's another atom. Of course, periodic table doesn't show you the isotopes. There's these things called isotopes, which are the same gas, the same molecule, or same atom, but different mass. And that's because they have a different proton number. I'm sorry, a different neutron number.
And that means they're heavier.
Well, yeah, they're a little bit heavier. Yeah. And sometimes we take advantage of the fact that they're slightly different in weight, too. Yeah. Yeah. In this case, we're taking advantage of the fact that they come from a different place. So helium-3 is really coming out of the deep mantle and less so in the shallow mantle and very little in the crust. But it's continuously coming out. There's very little left of it. Helium-4 is being produced in the crust.
So you know it came from a different place.
Right.
And then you can take a certain amount of water, and you can see how many 3s and how many 4s.
Correct.
And then you know where these gases are coming from, and based on the proportion of 3 and 4, you can make some scientific conclusions.
That's correct. We're looking at,
wow.
Yeah, we can tell where it's come from and, what it, hopefully.
If I'm standing on the beach, I'm unlikely to think this up.
Yeah,
Well,
that's
I
right.
thought, did you think this up?
Did I think it up?
Yeah.
Well, I thought part of it up.
Yeah, that's really something.
Well, I mean, my piece of this is I'm trying to make an instrument that will measure these isotopes in the field, in situ. And nobody's done that yet. There's been various attempts at it. Japanese have been pushing very hard on this, and they've gotten close. No one really has a nice, portable, low-power instrument to do this.
So let me get it. So you know that you got to find the difference, the proportion of 3 and 4, because there's a whole world of conclusions you can make once you do that.
Right.
But you don't have an instrument that will actually do that.
That's right.
You believe that this can happen. I mean, you know there's a technology out there that will actually make that measurement.
Right.
But you have to make it in a way so that it works for you.
Correct.
Okay, so you talk to the engineers.
Yes.
And you design it with drawings and stuff and schematics and circuits and what
Right,
have
right.
you.
And I also have a scientific partner, collaborator, David Hilton at Scripps. He's an expert. He's got also 20, 30
Scripps.
years of experience in this area. And, he's very good at keeping us grounded, so to speak. We make sure we're doing it right and getting the right kinds of numbers that we need to get. So what I do is like the circus master, just trying to get everything all together and make sure all the acts are working properly. And we have so many technologies we're developing with this project. It's lots of fun. We're doing high vacuum technology.
This all goes into the device.
Right, high
all
vacuum
used in the
technology,
device.
because we have to have enough headroom to see a little bit of helium-3 and a sea of helium-4. The ratio is something like 10 to the 6.
Let's take a look at some of your
Yeah,
slides.
okay.
We
Let's
have
whirl the
slides
slides,
Try
yeah.
to make this, okay, there's one.
Yeah,
Why
that's
don't you give
this-
us a running description, okay?
Yeah, this is, notice the word towards. We're trying to get to this spot where we can have a ability to measure 3-4 ratios. And we already know it's a key parameter in volcano monitoring. And these are myself, of course, and David Hilton at Scripps are leading this effort. So
Okay,
we'll go to
next.
the next slide. Why do it? Well, we think there's need for this in real time, and it has to be remote. For a lot of the places are remote and in the field.
Does that mean wireless? No.
Not necessarily wireless. I mean, there could even be a power cord nearby. That would be ideal. As far as communication out, that's easy. I mean, we have that technology already, so that's easy. I don't even think about telecommunication. I concentrate on the other parts that we really need to develop.
Right, now you're not talking about something that moves like a UAV or anything.
No,
This
no.
is stable.
You could put it on. You could put it on.
I guess you could.
Sure, right.
Sure.
Why not? Why not?
Next.
Next slide.
Okay,
Oh, this is just to give you a little background as to why it's important. This is Yellowstone, hot spot on the middle of the North American continent, and there's Old Faithful there on the left, and over there on the right is a sketch of what the magma under Yellowstone is doing, and this is from a paper by Husson, came out a few years ago, and he shows that gases are building up under the caldera, which is kind of scary on its own right because gassy things like that underneath the hot areas like that tend to sometimes explode, and there's plenty of evidence in the geological record of this
so how does
happening.
this relate to your work?
Well, because we're interested in being able to monitor a place like this for its helium isotopes, and I'll show you that in a second. Go to the next slide.
Next slide.
This is just to show you, I hope it doesn't end up just being yellow, but I guess it is. Anyway, that one's not coming through, but that was to show you how much has happened in the past in terms of the spread of the explosions.
The explosions.
Yeah, they've had some caldera eruptions there that have basically blanketed the entire North American continent, and that means nowhere you'd be safe. I mean,
This is just magma gas
everybody
coming out of the earth.
Yeah, this would be throwing a lot of rock material all over the place. And if you're in Florida, you might be safe, but if you're in Missouri, there's the question of whether you'd survive it.
And this could go, what, hundreds, thousands of miles?
Oh yeah, easy.
It's like a huge, big volcanic
It's
eruption.
done it in the past, and we know it's going to do it again in the future. It's just,
Really?
oh
It
yeah,
has
absolutely. No, there's no question. It will happen again. Whether people are around or not to witness it is another question. But
wow.
yeah, most definitely will
I
happen
guess,
again.
we have to remember that the magma in there, the composition of the earth below the surface, and the heat and the pressure, that's the same as it was many, many, many
Yeah,
years
it's
ago.
slowly building, and sometimes they eventually get to the point where it's critical. And that's what we want to look at. Is we want to see, well, if it's critical, maybe we could save a few lives. That's the whole idea.
Okay, what's the next slide?
Okay, this is from a recent paper last year from Jake Lowenstern and others. Came out in Nature. And what you're looking at there is that's Yellowstone again, looking right down on it. The caldera is outlined there. There's Yellowstone Lake. And all those dots you see are stations where they've collected the helium-3-4 ratio. And you can see the red there is an area where they have very high ratios of helium-3 to 4. So what this tells you is that that area is getting mantle gases. It's coming up from the deep mantle. That's the only source of those kind of ratios of something like 15 and above.
So I'm getting something now. Helium can be in the ocean and it can be on land.
Yes.
Helium is everywhere. It
That's
just
correct.
comes out of below the mantle.
The helium-3 does on its way to outer space. It's
Okay.
just a continuous process.
Is helium has special properties, characteristics that let it go through porous substances?
It does move faster than helium-4, we've found out.
Interesting.
Yeah, we're finding out all kinds of interesting things about helium-3.
Because it's lighter.
Huh?
Because it's lighter.
That's because it's lighter, yeah. And it has interesting quantum effects, too. So it gets really interesting at the quantum scale.
Wow, you learn things along the way then.
Absolutely. I never thought I'd be involving myself in quantum physics, but it looks like I might be. I never thought I had the credentials for that. So.
Okay, next one. Let's see what we got.
Okay, here's an example of what we're up against. These are all the arrows in our quiver. We have seismology, which is sometimes premonitory. It's most heavily relied upon method by far, and for volcanoes and earthquakes. Inflation, which is sometimes premonitory, which is, the slow
Gas
buildup.
pushes the surface up.
Right, and we have the heat. Sometimes the ground just simply gets hotter, and we can measure that very precisely. Radon, I mentioned before, is a gas, a ground gas that's also from decay of uranium and thorium. And it's one that people worry about concentrating in their basements, in granitic areas like Colorado. They have all these radon kits so that they don't overexpose themselves. So, but that's just in the crust. That's not going to tell you much about what's going on in the mantle. Helium-4, any helium isotope is going to come from deeper and have a farther reach. And that's why we're interested in helium. And then the 3-4 ratio in particular has been shown to be premonitory. In some places, it's actually been picked up just before an eruption. So that's why we know from just collecting that this is a good idea. And all I'm trying to do is just get it to where we can do it in a predictive mode.
Right. So let me give you my impression.
Sure.
So here we are at Yellowstone,
Uh-huh.
and we see all the smoke and stuff coming out of the geysers there and everything. And you have your black box, and your black box is deployed on the surface,
Yeah, we can put it on the surface, sure.
and it's reading the air. But in the air is the helium-3 and 4.
Right, you find
And
a
it's
gassy
making
area.
measurements of how much 3 and how much 4, and you have developed algorithms that will give you some advice based on what those proportions
Yeah,
are.
you could set that up to where if you saw a certain level, it's increased above a certain level, that would get your attention. Alarm would go off somewhere. And
3 or 4 or both.
probably the 3 relative to the 4 if it started to kick up a bit.
Yeah. Now when you have this, proportion, it only says X against Y. I mean, it's all
Right.
it's telling you, and you can make conclusions on the basis of that data
Right.
as to whether there's going to be an explosion. Is it
Yeah,
true?
that's right, because we normalize it to the air. Air is a beautiful standard. It's very well mixed. It's always the same everywhere on the planet.
Yeah.
And we use air as our standard, so everything's ratioed to air. And so air is 1 by definition. And we just look for variations from that ratio.
So what's a variation that would give you a lot of concern?
Oh, I'd say if you're in a volcanic area like Yellowstone, and if you're in an area where typically you see values of, say, 10 or 15.
10, 3 to 4?
Yeah, 3-4 ratio of 10, which is not unusual for the outgassing in an area. If it started to go up even a few notches, say to 11 or 12, that would give you cause for concern.
And okay, let's assume that you have your box perfected. I still want to talk about what's inside.
Sure.
You have your box perfected, and you know that the ratio is now 10. Something has happened. It changed, and it sends you a little internet alarm thing,
Yes.
which you get on your cell phone, right?
Yeah, you can do that. Have an app,
Yeah. It says, Gary, there's a problem here. What do you do?
Oh, well, I mean, what I do first of all is I try to verify that that's a real signal, and we'd have to check the instrument. we'd start looking at the seismicity, which we're not going to throw that data away. We've got it, worked really hard for it. So we'd be looking at all the other standard techniques to see what else is correlating with it. If everything's correlating,
You want to have more. You want to have a validation.
right. If you start seeing correlations, then there's cause for a real alarm. So then you would, at that point, what I would do personally is I would start calling people that might be have some authority to move people out.
Government people.
Yeah, probably people in the area that are in charge of moving
I
people
see a
out.
movie coming out of this.
Oh, sure.
I see Dustin Hoffman.
Yeah.
I want Dustin Hoffman.
Okay, yeah, he can play me, yeah. Put some high heels on him. Yeah, it would work. But, yeah.
That's great. Now, convert that for me from Yellowstone to right offshore here in Oahu.
Oh, well, see, here we have all kinds of hazards. It's almost scary thinking about them, but, you know, we have active volcanoes in the Big Island that if they erupt, there's always a chance that they might do something really nasty, like drop half of their mass into the ocean. It's just it's a very scary thing. I don't want to alarm people, but there are, certainly, we have world-class hazards in Hawaii. And those are some of the ones we have. And one of them, like volcanic eruptions that trigger other things like tsunamis.
And we can tell.
Local tsunamis. Yeah, right now we're not looking at these things, but if we had the ability, we could start looking at them with the isotopes. I think it would be very
Same thing
useful.
with the San Andreas Fault.
Yeah, oh yeah.
You'd be able to tell when it's going to go.
My colleague Dave Hilton has actually got some monitors out now on the San Andreas, looking for changes in the 3-4 ratio. So we know that it. You know, his kind of technique will not predict it, but if he sees it, you know, it'll add more credence to what we're doing. So it's being done.
At the end of this narrative, though, these boxes will be deployed hither and yon.
Yes.
There'll be a centralized alarm system.
Yeah.
And you'll be able to collect data and validate data on a sort of geographical mapping basis, right?
Right. I would like to see it, and I hope I get to see it before, you know, my time on Earth is over. I'd like to see it to where, you know, we have a network like that, and this is involved in it. Because we need all the help we can get.
Yeah. Let's go through the rest of your slides.
Yeah, I had some more of the, this is showing you, we talked about the ratio, how the nomenclature of it is. Air has got a ratio of 1.4 times 10 to the minus 6, 3 to 4. That's just a number. So there's one, for every one helium-3, there's like 1 million helium-4 in air. Ocean water is about the same as air, it's 0.5 to 1. The crust, ocean crust, is from anywhere from 0 to 8, depends on the age of the rock as it decays. Uranium decays in the rock, it adds 4, so it dilutes the 3-4 number. Arc crust is 5 to 8. Continental crust is usually very low because of all this radiogenic. Helium-4 mantle is 8.
So these are the normal numbers.
Yeah, now look at hotspots. They're anywhere between 10 and 35. Loi'i is right up there at the very highest one at around 35. So Kilauea is typically about 15. And by the time you get to Mauna Loa, it's already dropped to about 8. But it's still high. The only thing that's really high compared to the mantle, deep mantle, is what they call IDPs, interplanetary dust particles, and the moon's regolith. People actually talk about mining the moon for helium-3 because it's bathed in the solar flux, the solar wind.
Same technology.
Yeah, well, it's just being accumulated there, so it's probably mineable amounts of helium-3. If people talked about that.
I think people forget that in our solar system, the table of periodic table of elements applies.
Oh yeah.
And therefore, helium is everywhere. There's no reason why helium wouldn't be out on the moon. It's perfectly fine.
Especially if it can stick. If these things can stick in the regolith, apparently they can. They don't move as much as we thought.
So this kind of technology would apply throughout the solar system.
Yeah.
Could be useful in space travel, what have you.
We'd like to at least get it to where it works on Earth.
First things first.
First things first. If you go to the next slide, I think I have some slides. This is a really important paper by Yuji Sano and his group in Japan. And this is a volcano offshore, a volcanic island that they were monitoring for helium-3-4 in the water. And you can see the arrows are when they started having earthquakes. And they kept monitoring, and sure enough, they saw an increase in the helium-4 ratio. The 3 went up relative to the 4, and then slowly started to decay out or drop out, probably because the gas is moving, the three's coming out, and there's only so much helium-3, so after a while, it's getting less and less relative to before. But in a different place, this high school showed a different trend. So it's a little bit complicated, by the surface groundwater and the retention. But the general signal is there, you can see it. If you go
This helps you understand the relationships.
Tells you right there that there's got to be there's something going on. It's showing you the magma, fresh magma coming up has a lot of helium-3 in it, and that showed it to you right
Learning
there.
experience for you.
Yeah.
Okay. What else? Got
You
more?
got- okay, this is our closer to home. This is Mammoth Lakes, Mammoth Caldera, over in the just south of Lake Tahoe, on the Nevada side. And this is a great paper. It came out by Ensori et al. In 1993. They were collecting samples of helium-3 to 4, and they ratioed it as R to Ra. That just means it's normalized to air. And you'll see that over time, it's running around between 4 and 5, and then they start having a lot of activity. This was magma. They know it was magma moving around, harmonic tremors. And then look what happened to one of their stations. It shot up to like 6 to 7. So you were asking me earlier, would that be a cause for alarm? You betcha. This is cause for alarm because it might erupt.
It's confirmation of the science.
Right, absolutely. So this was done again by bringing samples back to the lab and analyzing them with a standard mass spectrometer. So by standard, I mean a pretty big one, like a sector.
We're going to take another break, okay?
Okay.
That's Gary McMurtry. He's a professor of oceanography at SOEST, the School of Ocean and Earth Science at UH Manoa. Here we are on a research at UH Manoa, and we're talking about predicting seismic events through dissolved gases. More to come. In fact, when we get back, we're going to talk about this black box. We're going to reveal all of Gary's secrets. Stay around for a minute.
That's right.
Hi, I'm Ethan Allen. I'm the host of Likeable Science on ThinkTech Hawaii. We talk about why people should like science, why science is actually fun, how science is a dynamic and vital part of everyone's life, why everyone, every man, woman, and child on the planet should really know science, should love science, should be familiar with science. So it's a great show. People come on here and have interesting conversations with us. They tell us why they do what they do, why they love it, why we should love it too. I hope you'll join us every Friday, 1 to 2 p.m. And of course, you can see it anytime on YouTube. Aloha.
Okay, we're back with Gary McMurtry, and now we're going to look at the black box. Here's a picture of the black box, at least one of the iterations of the black
This
box.
is actually, this is my colleague Dave Hilton's version of this. This is you see the copper coil in the bottom photograph?
Uh-huh.
What they do is they have a pump that he's showing you there in the top photograph. That's a syringe pump. It moves up and down.
Yeah.
They power this thing at a fault zone wellhead there, and they're pumping water from the groundwater through that coil continuously. And it's interesting how this works. They found out that they can stretch that coil out and chop it up, clamp it off, and because of the poor conductivity of the gas in the water, because of the length through to diameter ratio thing,
Yeah.
You learn this stuff in like physics. Anyway, they can clamp that off and they get a record for that particular time period. So it's a way of doing time series,
Taking a sample. It's a
samples over time. But of course, this is all brought back to the lab. Several weeks go by, maybe months, and then you get the data.
You can
right?
see what you
So
got.
that's state of the art. That's what we're doing right now. And of course, what we want to do is take it a little bit further than that. So
Yeah.
Dave always kids me. He goes, "Oh, you're going to put me on a business, Gary." And I said, "No, not really. Be plenty of
Take your
room
along
for
with you.
yeah, there's plenty of room for ground truthing.
So, but go back to that. What is the technology by which you measure the proportion of helium-3 and helium-4?
Well, we use mass spectrometers, and they're really
spectrometer. Okay.
Yeah, it's a spectrometer, and they're very sensitive, and they have high resolution, and they make them very small and low power now. So what we're doing is we're replacing a really big instrument that's the size of it's bigger than a washing machine. In fact, it's a lot bigger. The smaller ones are the size of a washing machine. So to give you an idea,
How
of
big
the
are
size
the
of
ones
them.
in your current equipment?
Oh, well, one of our mass specs is about
That big?
maybe 6 or 8 centimeters long. It's really small.
And you run the gas through something that the spectrometer can see through.
Yeah, what we do is we take a really small sip of the gas,
Yeah.
and then we can analyze it.
Okay, then you analyze it, and it tells you how many atoms? Does it tell you how
Yeah,
many
it tells
atoms?
you how many, it tells you an absolute number of how many, and of course what it is. How many twos, how many threes, how many fours.
All at the same time? Or
All at the same
does it make
time.
two separate readings?
Well, it scans, but extremely fast. So you don't even see it as a running scan. You just see a flash. There it is. So that's how fast
And
they
it
scan.
rescans over and over
Rescans,
again.
yeah. We're using scanners, and of course there's a little bit of uncertainty with scanning, but not that bad. And we can calibrate out all this information, so we can deal with that.
Okay.
And that's
then
where.
that signal is going to go on a disk somewhere in
Oh
electronic
yeah,
form?
that part again is it's pretty standard now. We're able to grab that stuff and put it on flash and store it, and also we can bring it out in real time too.
So you're essentially making a spreadsheet of all these multiple readings.
Absolutely, you just get like an Excel spreadsheet, a whole lot of rows of every sample, and then across the top would be the columns, which would be the different masses.
And so it's dynamic. In other words, you can take a lot of these readings and have you can see how it changes.
That's right. We're looking for
over
changes.
time.
That's right.
And that's information you would like to have.
Absolutely, yeah.
Very interesting.
So,
So in order to make this black box work, you got to have the readers. You got to have the device that puts the gas in front of the readers.
correct.
You have to have a little computer affair that takes the information from the readers, puts it in a database of some
Right.
kind.
Right.
And then you have to have the box completely secure so it's not going to
Sure.
be contaminated in any way.
We can usually do that pretty easily. We can put it in some kind of a hermetic seal, and that's
Yeah.
easy to do.
Where does it get the gas?
The gas.
Or is it
we're-
water? What's coming in?
Well, what we're doing right now, we're calibrating on air, so we just use lab air as our standard. But what we would do in the field, if we're interested in dissolved gas, is we would put in a system that would allow us to capture the gas that's in the water, and there's lots of little membrane-based technologies for that.
Fuel cell.
Yeah, kind of, not quite, but
Passes
it
through.
uses fibers, and they bring the gas across the membrane, and you can put that into your chamber.
So is it getting smaller?
Oh yeah. In fact, I'm not too worried about shrinking it.
Oh, you've already reached the size which is perfectly workable.
That probably would work right now in the field as it is, but it needs to be a little bit more trimmed up for the field. But it's kind of stretched out a little bit in the lab. But
And it has batteries inside.
we could run it. Yeah, there's some internal batteries, but mostly we'd run it on an external battery of some sort. A lot of wellheads, have power.
Sure.
There's pumps in there that need a lot of power, so
Sure.
we could easily tap off on somebody's AC. Now, you probably want to have a DC system, so we would have it set up to where we would have a battery backup, and we would just be trickle charging our batteries with the AC.
So what do you need DC?
Because in earthquakes, the first thing that happens is you lose power.
Of course.
So we want to be able to continue to sample through that, so we would have set up our own.
So if you're using external power, you still want the direct current.
Yeah, we always make our machines
That's what
DC,
runs
direct
it.
current.
And it's, 12 volts, something like that, the standard 12?
We use 24, it's a little bit
24.
more efficient, yeah, 24
Okay,
volt.
okay, right.
That's no problem. Yeah.
All right, and the idea is, right now, you're going to be carefully deploying them one at a time, but going forward, the
Right.
idea is to have so what does it cost to make one?
Oh, I would say you start around 50,000 US dollars, and typically, more things you add to them, it's a number between 50 and 100 is about what gets you the hardware. And then if you want me to work for you, you got to pay me
yeah.
something too. So, they're not real cheap right now, but, there's economies of scale. So if you had a design we liked, we can make them a lot cheaper. I think we can get them down probably below 50.
Well, have you, this reminds me of a gizmo that was developed at the university, which was a bunch of sensors on some pontoons and UAV technology where you could send it all around the harbor and it would sample water, with threat water, or chemicals, what have you. And what's interesting is that they found a company on the mainland who would manufacture it, and spring the bucks necessary to do that because it isn't cheap. And then they were going to sell it. I don't know what happened, but that was the plan.
Yeah.
And I'm thinking that, every device that comes up like this could be popular. And my question to you is, do you think this will happen? Is it happening? Are you getting calls and letters all day?
not exactly, but I've had interest from people in NOAA and I've had interest in people in the U.S. Geological Survey, and those are a couple of prime
Sure.
customers for us
Yeah, yeah.
that we would want to convince. You
Yeah.
know. Well,
So
first,
is
we're in
it
the process of convincing ourselves right now.
So
Once
it's not
we're
really
convinced,
perfected yet?
sorry.
Not really perfected.
No, we're still in the R&D mode, but we now have a prototype, and that's a really important step. We have one. We know how to make them. You know, we're getting data off of them. That's what was really counts.
So we only have a minute left, but
Mm-hmm.
I'd like to ask you what the future is for this, and the future for your involvement with it. You've been
Well-
at it 15 years. Are we beginning or are we ending?
I think we're getting close to the end. I mean, I think it's a few more years, and we'll have it to where we can get it in the field. It'll be fun to at least be around to see how the field deployments go, and you know, kind of quality checking on the data as it comes in.
Yeah.
Yeah.
You can tell us how it goes time to time,
Yeah.
and see the level of interest from NOAA or whoever else. You know, it could be useful anywhere in
Oh
the
yeah.
world.
If nothing else, it can replace our big bulky instruments with a smaller one.
Yeah. Well, and as the world, changes, or we get more sensitive to the changes, and who knows what climate change will do, we need to have a better handle on exactly what's happening under there.
Oh yeah.
So
I
this
think
is one
so.
way to do it.
Yeah. Thanks.
Thank you, Gary.
Well, thank you.
Great to talk to you.
Well, good talking to you. Thank you for having me on the show.
Absolutely. Gary McMurtry, professor of oceanography at SOEST. Really enjoyed talking to him. We'll be back next week with another professor at SOEST. I don't know who yet, but it's coming soon.
All right. Great.
Aloha.